Quick, dude. We never know what you're going to do with it. Anything? Any questions? Homework? Homework stuff? You're all like, dude, let's just get to Wednesday. Say again?
Will we have any quizzes?
The only time we could, so the next test, let's just go ahead and talk about that. It's going to be Monday, the 7th, and then the 9th is our review day for the final. The last day of lecturing new stuff will officially be the Monday after. No, I'm sorry.
Wait, the 7th is a Wednesday.
December 5th, okay. All right, whatever the Monday is. So I definitely need you guys' help. Stuff. My calendar is currently either not here or doing something else. Okay. The 30th is the official last day I have to lecture over stuff, so the 30th is going to be a combination of finishing up whatever and then getting into review for the test. That'll be the following Monday. I don't want to just not do that last test because you guys should realize as students you want more grades, right? Obviously I'm going to have to cut some stuff out, so on next Monday I'll have an updated homework sheet that shows you the homework. I'm probably going to cut down on some of the homework in the last few sections we'll be doing and cutting some sections out.
Is it Stokes and Greens that we're going to be cutting?
I want to do Greens. I'm thinking maybe I'll cut Stokes, but I definitely want to do Green's theorem. We've laid the groundwork for most of the stuff you'd have to do, but we definitely have to talk about the curl and the divergence. I want to lay that groundwork. Some of you guys come in already having worked a little bit with curl. Anybody work with the curl and the divergence of stuff? A few people. The rest of you guys are like, what the hell are you talking about? Curl? Do I work out? Is that what you're asking me? No. Divergence? Do I go to the movies? I don't like. Yeah. What's up? Finals cumulatives, no question. Yeah. Yes.
Did you mention whether or not there was going to be another quiz before the next exam?
That's what I was trying to verbally figure out myself.
Okay.
If we take this Wednesday off, and then, the next quiz, the only time we would actually be able to do a quiz would be Monday. Or and some of you guys look actually okay with that.
Oh, yeah.
All right. You realize a week from today, right? Yeah. I'm thinking. I might do something I don't normally do. I might do a group quiz on Monday. Ooh, yeah. Ooh, that's different. What's up? Oh. Too bad for them. If they don't email me and tell me why they missed today, then too bad. Obviously, I'm going to send an email out saying for anybody that we're not having class on Wednesday and this is what you missed, because I'm way too nice. They could just show up here and go, "Where's everybody? What's going on?" But I don't want that to happen.
What do you think? How far do you think we're going to get?
Well, let's get in it and see what happens. That's why I'm going to give you an updated sheet on Monday. It kind of depends on what happens today. All right, is everybody with what's happening? Monday, we will have a group quiz. It will cover 15:6, basically up through. We really haven't talked about it, so I'll just cover the last part of 15. Since we're going to actually fully get into Chapter 16 today. We sort of got into Chapter 16, but not really. I just barely mentioned a few things on that handout. Let's see. Here we go.
I think it's 59.
So if nobody has questions, we're going to go right back on this handout then.
Oh, no. Yeah.
Oh, yeah. All right, guys. Mike, how old are you? Oh, yeah, I do now. Just now happened. It's perfect time. All right, guys, here we go. Anybody actually try this one out? So, I'm not going to go deep into that. I mean, this is actually easier than you might think it is. So now our inputs are points, and we should be used to that. We've had inputs as points before, but this is a slightly different usage of that. So 0, 0 obviously results in what? So everybody's cool with this? The one I'm looking at here, the bottom left-hand corner one? So 0, 0 is a 0. So let's try like 1, 1. So if my input's 1, 1, what does F become?
1 half.
Yeah, 1 half, 1 half. So at 1, 1, I can just draw 1 half, 1 half. So it's going to go like that. Is everybody cool with how quickly I did that? I mean, it starts at the point 1, 1, and then it just goes in the direction that the resultant thing says to go. Not a big deal. Now, what's interesting here is the y variable changes the resulting x component of the thing. So what gets more interesting is to see how it changes. So for example, let's say 1, 2. What would that be?
That'd be 1, 1 half. 1 half.
Yeah, be 1, 1 half. You guys see that?
Yeah.
Because it's y over 2 for the x component. So at the point 1, 2, it's going to point 1, 1 half, right? So as y grows, what happens? What happens to the resultant vector at that point as the y part gets bigger? Starts getting longer in the x direction, right? And then the same thing happens with as x gets bigger, it starts to get longer in the y direction. So if I keep going up, if I go up to the next one, 1, 3, let's go 1, 4. Why not? Let's screw fraction. What's 1, 4 going to be? I'll screw fractions.
2, 1 half.
2, 1 half. All right, just plugging stuff into the equation. So now it's at 4, it's going to be 2, 1, 2, 1 half. It's going to be 4. So as I leave x constant and I move along y, it's the x part of the answer is getting larger, and the y part is staying the same. I like it.
Can you do the
So-
last one more time, please?
Okay. So if it's 1, 4, so I call that poor little 4. It's just never going to be a 4. 1, 4. Plug in 4 for y, you get 2 I hat plus 1 half j hat. Is that cool? And then you still from the point 1, 4 you go over 2, up 1 half. Bam. That's the resultant vector starting at that initial point. I like it.
Thanks.
Anytime. So now let's look at let's look at like let's go this way. Let's go. What's 2, 1 look like? Yeah, I like it. So it'll be 1 half 1. So at the point 2, 1, I'm going to go 1 half 1. Is that cool? Or you can go, up 1 over 1 half. Okay, I like it. And just like we said, if we leave y constant and we let x increase, the y part of the resultant vector gets larger. That's what happens when you mix those, the y pieces in the x part, the x things in the y part. Okay, I like it. Maybe. So I can kind of make a prediction here. This one is probably going to look like, it's going to be a little bit higher and a little bit higher. Okay, I like it. Not perfect. And then for the negatives, you can do a few for the negatives also. So let's see real quick. If I do -2, -2, what's that going to be? -1, -1. I like it. So -2, -2. It's going to be -1, -1. What about at -2, +2? What's that going to be? Gotta be careful now.
1, -1.
1, -1. I like it. 1, -1. So here at -2, 2, it's going to be 1, -1. That's some freaky shit. So again, if I leave the x constant and I change the y, then my x piece is going to get, and I increase y, the x piece is going to get longer and longer. So just to show you, if I did -2, 4, what's that? What happens there?
2, -1.
2, -1. So at -2, 4 is pointing to -1. So as I increase the y piece, the x part of the resultant vector gets longer. All right. But really, this kind of thing just involves there's very simple calculations. But if you do enough of these, you start to get a feel for what the result's going to look like for a given vector function. And so, I mean, you really just have to do this one on your own to see what happens. Now, what's more interesting to me than this, because this one you can just calculate and brute force it and draw the little things and then look at it and go, well, now that makes sense. This is a much more interesting question to me. I mean, this is the back of this. Right? And I think it's actually a little easier just to start looking at these and figure out which one of them these are. So like x, I, that's all I want. So really this is going to be the point, this is the vector function that takes x, y, and it takes it to x, 0. Is that cool? 0 j hat. Which means, can somebody tell me something about what that would mean visually? What's going to happen here?
It's going to be all in the same direction.
Well, no. For positive x, it's going to be pointing that way. For negative x, it's going to be pointing that way. Right? Whatever way was right for your perspective. What's more interesting, though? Yeah, y is going to be... There's no... Not only is there no y component, there's no dependence on y. So what does that mean? There's no dependence on y. So it means...
No up or down.
Once you figure out 1x, it's going to look the same as you go up and down. So if at this point it's like this, at this point it's going to be like this, at this point it's going to be like this, at this point it's going to be like this. Because the y part has nothing to say here. You got to see that. So this kind of thing has happened throughout math. You got to stop and realize when something has no y dependence or no x dependence or whatever, that actually tells you something visually. So which one of the graphs must A be? Yeah, that one totally agrees. As y changes, the little arrows don't give a shit, right? That's what we just said. But as x changes, they totally give a shit. It gets a little bit longer as it goes back. And these have been scaled, I think I said at the top, thank God, scaled to fit, right? So that's going to be A. What about B? What's freaky? What's a little freaky about B?
It's constant.
Yeah, it's constant. So no matter where you are, period, it's got to point in the direction to -1.
Is it C?
Yeah, so that one looks like it's pointing in the direction of 2, -1. No matter where you are, point-wise. So the difference between this, it does change as x changes, but it does not change as y changes. Here, it doesn't change no matter what the hell you do. I like it. You guys semi with me. This is actually not that big of a step from anything we've ever done before. It's actually, maybe some of you guys are going, oh yes, please, do a lot of this. Maybe you are, if you realize what's happening. This is not that evil. So that's going to be B. What about C? So this one's going to look like x, -y, right? So why do you think it's A? Somebody said A?
And they're always moving in like the opposite y direction. Like they're moving in like the x direction, but like the opposite.
I like it. So along the x-axis, y is 0. So we've done this kind of thing before with like the paths to take to look at limits and shit. So along the x-axis, y is 0, so it should only care what x is doing, right? If I change y, if y goes up by 1, this is actually going to react by looking down 1. I like it. So that does kind of make sense. So you can actually investigate some of these by thinking, okay, what about along the axis? And then you can eliminate some of the other stuff, right? Along the x-axis. Along the y-axis, it should just be doing 0, negative y. So as y gets bigger positive, it should be pointing down more, right? Okay, I like it. Sweet. All right, okay, maybe. Or some of you guys, most of you guys are shaking your head. Yeah, some of you are looking at me like, why can't we have the whole week off? See. Now this guy here, this is kind of like what we just did, where it switches the y and the x pieces. So now think about this real quick. Even if you got the answer already. Along the x-axis, well, let's do this first. Along the y-axis, what's x? Along the y-axis, in general, just for whatever. Along the y-axis, the x is 0. I like it. So along the y-axis, this should be y, 0. So like at the point 0, 7, or let's say 0, 2, it should be pointing... So along the y-axis, x is 0. So it's going to be y, 0. So at y = 2, it should be pointing in the direction 2, 0. Right, so at y = 2, it should be pointing 2, 0. At y = 3, it should be pointing 3, 0. Maybe. So, I mean, then there's a lot of other ways to look at this. You could just start plugging in points and comparing them. I like to look at axes to kind of get straight to the point. If I'm so along the y-axis, it just looks like y, 0. Along the x-axis, what does it look like? Along the x-axis, what's 0? Y is 0. So this is going to be 0, negative x. So if I'm at the point 3, 0, it should be pointing backwards along the x-axis, right? Or I'm sorry, down. So if I'm at the point 3, 0, it's going to actually be pointing 0, negative 3. It's going to be pointing straight down. So it's like pointing orthogonally to the axis. So which one seems to be doing that? So, it's not quite this one, right? Because what we say, like at the point 0, 2, what should this be? At point 0, 2, it should be pointing 2, 0, right? So what's unfortunate about some of these is they don't give us like what's happening at the axis, like which one I was looking at. This guy doesn't give us exactly what's happening. But look at this guy. Now, we haven't looked off axis yet, have we? But this is the only one so far that does what we think. Along the x-axis, it's supposed to be pointing orthogonally to it. Right? And along the y-axis, it's supposed to be pointing orthogonally to it. And then if you think about... Then you can just start plugging some points in to see what it's going to be doing along some diagonal. Yeah?
You can also just think when y is positive, it's going to be pointing in the positive x.
I love it.
And when y is negative, it's going to be pointing negative x.
So now you can start making generalizations about, whenever, for example, where is it? Whenever x is negative, it's got to be pointing up, right? So here, x is negative back here, they're all pointing up in some way.
Yeah.
Do you see that? Good, I like it. So you can start to make you start with the axes, you can start making broader generalizations about the components of the vector, at least. All of these vectors definitely have an up component to them. All of these vectors definitely have a down component to them. I like it. So I think I said before last time, but it might have been really quick. When you start mixing the x and y stuff, this is where you get this neat motion, this neat rotational motion. So then we got D is going to be this guy. And then E, yeah, YB. Because now they just go with each other, right? The y part influences the y direction. Right? The y part is influencing the y direction, the x part influences the x direction. So as y gets bigger, it's going to be pointing in the y direction more, and so forth. I love it. So it's got to be B, kick-ass. I don't get that rotational motion like we just did, because it's not a mixing of the variables, and the plus and minus. So there's E. And then remarkably enough, that last weird little dude, it's got to be F. Thankfully that one was last. But again, you can just kind of do a few. You realize that this is just what's true about the x component. It's always going to be twice the y component, right? I like it. So you can start realizing how it is out here was just a process of elimination.
You can also see that there's the line there that's defined by y equals 2x.
Exactly.
And whenever it's above the line, it's pointing in that way.
Kick ass.
Below, it's pointing that way.
There you go. So that idea that the x component is twice as big as the y component with an opposite direction, you can actually see that influence here. So there are more generalizations you can make. I like it. But it just takes getting into it and trying some of those problems out. That's 16.1. Let 16.1 be nice. Please do God. It's either brute force, make a little table of values where your inputs are points, but that's old news. The outputs are now these fields, but we realize we've already dealt with fields. The gradient is an example of a field. Because the gradient is a vector defined for any point you want to plug into it, where it's defined. Do you guys understand? So we can actually take any gradient we've ever done, and I won't give you an actual point, and you just figure out where it's pointing at each point in its domain. And then you've just created what we call a gradient field. It's crazy. Okay. So that's 16.1. Let me see if there's anything specific I want to talk about there. Here we go. Oh, here. I'll give you a few quick physical examples of these. So besides, like science fiction, but there are things actually called force fields, but we have specific types of force fields. We have one that thankfully is there for our satellites and for, life in general. So we actually stick to the surface of the Earth, or we want to go to the center, but thankfully the surface keeps us from doing that. Right? That's nice. Thank you, surface of the Earth. And of course there I'm talking about the gravitational force, right? So the gravitational force field. This will be, so if I have if I'm talking about a point x, y, how do I say this? That doesn't matter. Yeah, you can do x, y, z. So we're going to call it x to be the vector that points there. Now in physics we just use r. I like it. There you go. But then we have this negative m, g. I love g. It's just the constant that makes it all work. Over. All right, now some of you guys might balk at this a little bit, but you have to realize something about how you can play with these two things. To be honest, here's what's really happening. Now that makes it a little more familiar. Some of you guys might know this formula as this. Not thinking vectorially, right? Just thinking pure, straight up. Here's the center, and here's the thingamajig, and there you go, and it's so far apart, right? So this is really, so there is a cube there in the formula, but now when I pull this out, this of course is a direction. I love it. It's a unit vector which only supplies direction, and there's the actual force that we're used to in that direction. I like it. This is a field. It defines for every point in space, it defines a vector, and so the outputs are vectors.
What's the big M? Is little m mass?
They're both masses. The big M is normally considered to be, it's a big M, so it's like tiny satellite, big planet. So M is the satellite, big M. It doesn't really matter, right? Just need the two bodies that you're talking about, the little fudge factor there, or the physically determined by observations constant, and then the rest of it. I like
And then that's the square distance.
Yeah, so it's that inverse square law that we see a lot of with like sound and light as it goes away, has to paint the surface of a sphere, and that's why you have so many things that are over r squared. Or not. Okay. And then the really cool one that looks a lot like this is the electric field. And let me build my way up to that. Let's first talk about the force due to a charge Q on another charge. Little q. Does this sound familiar? Let's see, this is this one. So Q. I like it. This is, by the way, this is in the book. This is on page 1112. They don't get too much into what this constant is, but if you've taken some physics, you know what that is. That's the force due to a charge. Now, what's interesting is, I like the fact that we look at what we officially call the electric field is just doing 1 over Q times that force field. So then you just end up with the same thing, just missing a little Q, because you have a big-ass Q that you put somewhere. I just call it big-ass because it's capital. I could just say capital Q, but it's not as interesting. And it sets up this electric field. So if I do put a charge near it, it'll experience this force. So we like to think of it before we have to put that charge there. There should be this like potential waiting to act on something that I put there. So there's this electric field that exists around a charge. If I do put a charge there, it experiences this force. How much of this do you actually care about physically? Hopefully a little bit. But for the homework, you just have to be able to plug and chug and get expressions and work with it. Yes?
So that seems to almost be like a spherical field as opposed to like these weird things that we see. So where does that come from?
Well, if I put 2 charges down, then their overlapping effects will create interesting, and depending on their relative strengths, that's where you start to get really neat. So if I have a single charge at the origin, it's going to be very nice and symmetric. There's no reason it should be different. I like it. Cool. Same thing with magnetic fields. All right.
Yeah.
Poor magnetic fields. All right, the last little thing in this section. So, I mean, I went a little quickly here because this is not a physics class, so you don't have to totally understand every little bit of this. It's really just a formula that you can use to plug stuff into from the mathematical perspective. But I also like it because it gives you, it really makes you realize that this math that we're doing has obviously automatic usefulness. What we're about to do is, if I'm given a field, and I'm gonna, let's say I'm given some field, a gravitational field, and I'm gonna go through it with my little spacecraft, and there's a certain route that I want to take. I want to be able to calculate, I want to be able to use something that calculates, well, how much power I'm going to have to use to get through that, how much work am I going to have to be able to do to get through that gravitational field in the direction that I want to go, those kind of things, right? Cool. Interstellar, how close can we get before we get sucked in, all that stuff. And get behind the bookcase and weird shit. If you haven't seen the movie, I'm sorry.
Ghost Matthew McConaughey.
I gave myself the message. Okay, sorry. Spoiler, sorry. So the last thing here is a gradient field. I really think, if I plot out a gradient field for a given function. So what's interesting about a gradient field is it's defined for, all right, let me make sure you guys really get what's happening. So this is what kind of, let me do this little side note. This here is what kind of function?
It's a vector field?
Yes, beautiful. It's a vector field, a vector valued function. This is a vector valued function. It has vector outputs. So if I say a scalar function, or scalar valued function, What am I talking about? Somebody give me an example.
Like 2x, y.
2x. Sure, that'll work. Let's bring y into the poor little mix, right? 2x would work, of course. 2x by 7 would work. What the hell? Right, for every input, there's a scalar output. For every input here, there's a vector output. I like it. Hey, Mike. So real quick, when we have these things, this is my input plane, right? So when I'm talking about a scalar valued function of these two variables, at any point there's going to be some height, some output, which you can interpret to be a height. Are you guys with me? I've talked about this enough, hopefully. Where you get this surface that goes over and maybe dips underneath. So the difference between that and a vector valued function is every point has some vector that points off from it. It's amazing. Here I'm forcing myself to live in 2 dimensions, so the vectors have to live in 2 dimensions. You could certainly have a 3-dimensional vector field, and it's not a big step to go from there. It's a little bit harder to graph, obviously, right? Just a tad. All right, so what would the gradient of this be? 2, -1. All right, I like it. Right. So let me see if I can make this more interesting. So this gradient would be 2, -1. What would, and is that's at any point, right? So there was that example of a vector field that, I think it was exactly that, wasn't it? Was it that? No, it was definitely a little bit different. But this guy here, yeah, it was exactly that. There we go, 2, -1.